Hi, in this video I'm going to show how to use the Orca Compound Scripts module to semi-automatically calculate the stretching and bending force constants for a simple molecule. I'm choosing acetic acid in order to be able to obtain parameters for a simple force field for that molecule. This is just an experiment. It has a lot of manual tweaking, but in principle this could be automatized to generate a force field for a small molecule that then can be used in Orca or in another molecular dynamics package. So what I have here is acetic acid. This oxygen, part of the carboxylic acid, is labeled O2. The next one is O3, C4, and C5. But this is Chemcraft numbering, so in Orca we have to subtract 1 for each number. So this is oxygen, this is 1, 2, 3, and 4. And we have different stretching modes. We can stretch the 1,3 bond or the 2,3 bond, or we can flex the angle, the 1,3,2 bond angle. We can change that. There are several angles. We are not going to try to parameterize the oxygen H bonds or the CH bonds for simplicity, just to make a shorter program, but this could be also parameterized. So with this numbering in mind, we can make an Orca compound script, which is the following. I'm increasing a little bit the font size. This script was partially based on the iterative optimization compound script that is inside the compound scripts GitHub that contains many examples. And I'm also going to, in the future, use an example for relaxed surface scans that is in the Orca manual. There's a simple step. Step 1 is a single point calculation for which I'm choosing PV0 with def2 SVP. And this is stated here in this variable called method. Then I'm also setting other variables, which are the name of the initial coordinates, which I will call initial.xyz, and then the charge and multiplicity. And number of scans, I'm choosing to be 6 because I'm going to be scanning 3 bond lengths and 3 bond angles. And then I'm defining other variables. This is going to be a name for the output XYZ coordinates for the first structure. And then I am defining the scan array that has a length of 6 n scans. And each component of that array is a string, basically a set of characters, that contains the scan that I want to do. For example, geom scan B for bond 1,3, it would be oxygen 1 and carbon 3, the central carboxylic carbon, and I'm scanning from 1.1 to 1.5 angstrom, because I have previously seen in the structure that the optimal bond length is between 1.2 and 1.3. Then I'm scanning the 2,3 bond distance, that's the other oxygen, and then 3,4 is the carbon-carbon distance. And this is a little bit longer because this is a simple bond. And I'm also scanning different angles. 1,3,4 is going to be one of the oxygens and the 2 carbons forming a bond, and I'm taking to be the central in the scan to be the actual bond angle in the structure, and then I'm going on steps of 10 degrees on each direction. I am choosing for all the scans 5 points. The minimum would be 3. The more points we have, it's going to be more accurate to have the energy profile for the bond angle or the energy profile for the bond length. But the force fields are going to assume that the energy expressions for the bond lengths are going to be quadratic, the same as angles. These are harmonic approximations. So in order to fit a quadratic function, you only need 3 points, at least 3 points. You can have more, but the problem is that these have to be close to the minimum because the harmonic approximation is an approximation, and the actual bond lengths and bond angles have a more complicated shape, and they only approximate a quadratic potential very near the local minimum. So, but I'm going to show a little bit what the difference is going to be between choosing these ranges of values. So after this, these are only comments. What I'm doing is a new step, and this is basically a single point calculation that is going to generate charges and is going to generate a structure. Those charges are also necessary in any kind of force field calculation, molecular dynamics. And then I'm going to start a loop for I step from 1 to n scans. I am going to loop over the components of the array starting from 0. And then this is going to basically introduce in each step the variable. When we write this ampersand and a variable inside curly brackets, it's going to just introduce the variable in there. It's going to be text in this case. It's basically we are putting the geom_scan keyword on every calculation. And then it's going to just do a relaxed surface scan for each bond angle or bond length. And after that, it's going to end. So beyond that, we have to have the initial molecule. These are just coordinates that I copied from Chemcraft. So this is the molecule. We go to coordinates and I just copy this here into this file. 8 is the number of atoms, and I just put the name here. Is going to be a comment that is going to be ignored. I have an input file that the input file only calls the compound script. And also I put pal8 because I'm going to parallelize it with on 8 cores. And then I use one of the standard shell scripts that we use to submit calculations to the cluster. But that's basically cluster dependent. So it may not be useful for your setup. So these are basically all the files that we need. We need an initial structure and we need the compound script. This is a simple script. There's an example in the manual that has a lot of keywords for exporting things and even plotting things in Python. So I didn't want to do that because that was much more complicated and I wanted to keep this as simple as possible. So I have already done this calculation, and when I calculate this on the cluster, here I have a lot of files, of course, and many of them contain interesting information, but I'm going to just show some of the results of the files. For example, you can see here that we have all the name of the basically of the input file, dash compound 2, compound 3. That's the different numbers of jobs. Compound 1 was a single point calculation, so it doesn't have a relaxed surface scan. It will have other output files. But then for each of the 2 to 7 compound calculations, we have this relaxed scan, ACT, and SCF, which basically contain the actual energy containing dispersion corrections and other stuff, and the self-consistent field energy for each step. So for example, if we open one of them, we will see we have basically the energies for each of the bond distances from 1.1 to 1.5. That will be the first bond that we scanned. The others are the same. So what I did here is I plot this in a program. I plot the energy profiles. So this is in kcal per mole versus the bond distance. These are the bond length scans. We can see here the numbering of the atoms. So for example, we can see here that for the 1,3 bond, the minimum is near 1.3 angstroms. And we see in all of them like an upper concave function. It may be a quadratic function or it may not. And we are defining a function that's basically a quadratic function of the interatomic distance. DAB is going to be the minimum equilibrium distance. KB is going to be the force constant, and the D is the actual distance of the bond in the relaxed surface scan. So this is squared. This is a harmonic potential. So we can calculate KAB and DAB through fitting this function to this data for each bond. We can see here, for example, that the C3-C4 bond is much longer. It's 1.5 angstrom. If we go to the angles, We also can see like a more or less quadratic behavior. The lines are not fits, they are just, to help see the connection between the points. And basically we could fit the central 3 points with a quadratic equation. This is going to be a force constant for the angle ABC, and the theta is the angle, and theta ABC is going to be the equilibrium minimum energy angle. You can see here that for the oxygen 1, carbon 3, carbon 4 bond, this is around 110 degrees, but for the other bonds it's slightly longer. And we can see here that the energies are much smaller for the angles than for the bond lengths, which makes sense. Like elongating a bond has a higher frequency, for example, in IR than bond angle flexions. So in here we can see for the angles, these lines are now the least squares fit. Actually, I did not fit the angles. I manually changed the parameters to basically fit as good as possible the 3 lower points. And we can see that there are deviations for the longer distances. In this graph, I plotted from the minimum to the maximum distance. We can see here that basically when we decrease the distance, the energy grows faster than a quadratic. And when we elongate the bond, the energy grows slower than a quadratic, which is basically what we would describe as a Morse potential. So we cannot use very large ranges for bond lengths. We should scan at least 3 points and maybe even 5 points close to the equilibrium position. But we can see here that the longer the bond, the less concave the fitting function is. So that will tell us that the force constants are going to be different. And here the same for the angles. So what I'm doing here is putting the results of the different calculations. So I took the equilibrium bond lengths and the equilibrium bond angles from the initial structure, and these are the different pairs of atoms or triads of atoms. I have to copy in here the force constants that I obtained from the fitting. So for example, so here for the last scan, that would be 0.031. So this would be here. Compound 6 would be the 5th actual calculation, so that's 0.035. We can recognize here already have the equilibrium bond angles. For 5, it's 0.027. And here for the bond lengths, we will copy the first value. This is 430 for the third value, 430, 820 for the second bond lengths, and 500 for the first bond length. So now we have the force constants and the equilibrium distances and angles for all the bond lengths and bond angles. If we see here, the values are quite different for the bond angles. This number 0.027 is basically stated in kilocal. So the unit for this is going to be kilocal per degree squared. And this is going to be kilocal per angstrom squared. Okay, so these are the differences. If we had plot the angles in radians, these numbers would be larger. So that's an easy conversion to do, and I can show an example in Origin that I used. So in here, this is for the first bond angle. We can see here that if I'm using degrees as a unit, that's 111 degrees, I get a force constant of 0.027. Maybe we can increase. Maybe now we can see it better. So in degrees, the force constant is 0.027. But in radians, that's basically the angle. I'm converting it to radians by multiplying by pi and dividing by 180. The force constant is 88.6. So basically these give more or less the same number. So if I plot these two, we can see that they are very similar. So I can also add here, we can see that the lines are basically the same. They are different units, and these are the experimental points. And more or less I have a fitting on the minimum region. The fitting is not perfect. I did it manually. It was not the point. Still, this is far from being a very accurate parameterization of the molecule, but in the future, I plan to make a fully automated program to generate the compound script and then to read the output files and fit the energy profiles in order to generate the force constants. Small detail, sorry, this is kcal per mole. Kcal per mole here. So now we have not everything that we need in the force field, but we have some of the things. We can also define charges. O1, O2, C3, C4. So where can we find the charges? If we go here to compound 1 dot property text, in here we will find basically all the results from the calculation. And if we go here and search for loading, here we would find all the charges. So I will just copy the charges here. So here, for example, this is going to be O1, O2 here, C3 and C4 are going to be here, and the others are the H atoms. So H0, H5, H6, H7. So with these charges and with these bond lengths and bond angles, we could make up a force field. We are still missing all the hydrogens. We could extend the compound script. For example, here we could just add up more scans and scan all the bond angles and all the bond lengths, including the hydrogens. That would make the calculation take longer, but probably this was also fast. It took maybe 1 hour or 2 hours. And I'm using PV0 with D3 and Def2 SBB. We could also put just simply high force constants for the bond lengths containing hydrogen and not optimize the hydrogens in the molecular dynamics calculation. This is, of course, not meant to be an accurate description of the force field in the molecule, because there are many other things that are missing, and people have already done this much better. But the point is to be able to produce a simple parameterization that may be useful for a fast calculation on a molecule that's not already parameterized or not in the same kind of force field that we're using for other parts of the molecule. This could also be useful for the case when we do a QMMM calculation and we just want to parameterize a certain solvent or certain electrolyte or something that's not common. That could also be used for the MM part. So finally, just to show a little bit what we have done, I'm opening one of the Relaxophase scan results, and if I go here, for example, this would be the stretching of the carbonyl. We can see here basically that the force constants are not the same. The carbonyl, the O2C3, this is, remember the numbering, we have to subtract 1. This carbonyl bond has a much higher force constant than the other bonds, because basically it's a double bond, and the others are more or less single bonds. So that is all for now. I hope this has been useful for you. This is an example both of using the compound script model for complicated workflows, a little bit complicated, and also how we can more or less start to understand force fields and how they relate to calculations. And hopefully people will find it useful to build on top of this. I'm going to upload this to GitHub by the time the video is up. So thank you very much. See you next time.